Last time we stopped at this assignment. Now let's continue from here. Whenever we are speaking of any system, we will have some data producer in the system, which will generate data, and some data consumer in the system, which will consume this data. Producer and consumer. Now, the amount of cycles that a producer takes for generating data might be different from the amount of cycles that the consumer takes for consuming that data. So you might have a case where the producer is ready with the data, but the consumer is not ready to accept the data. So the producer has to wait until the consumer is ready. Or else the consumer might be ready to accept the data and the producer might not yet have the data with it, in which case the consumer will have to wait for the producer to generate the data before it accepts it. A transaction can take place only when both the producer and the consumer are ready in the same cycle. So the transaction can take place only in this cycle. So our condition is this is 1 and this is 1, which is basically an AND of both the readies. So let's do that. This is producer ready, this is consumer ready, and we AND both of them. And the result of this AND goes as enabled to the consumer and as enabled to the producer. So only when this enable is asserted on both the sides will this data transfer take place from producer to consumer, and then producer will prepare the next data for transmission. And similarly, consumer will consume this data and then make itself ready for the next data which will come in. Now, given that this is the logic for our producer-consumer interface, which depends on a ready and an enable signal, let's go back to our original design of an OR gate and have each of this input A and B come from two different producers. So this is producer B, this is producer A. And similarly, the output Y, let it go to a different consumer. So consumer of Y. And this DUT itself, on this side, it is a consumer, and on this side, it is a producer. For A now, we have a ready signal and an enable signal. And similarly, for B, we have a ready signal and an enable signal. And an additional change that we made to our DUT is that since we are not assured at what time this producer provides data and at what time this producer provides data, this might be two completely different times. So we will have a storage element over here of some depth X, which can store whatever data is provided. And similarly, at the time when this is ready with the data, this might not be ready to consume data. So we might have a storage element at the output, which can store multiple elements until the consumer gets ready. In this design, if we look at organization of producer, DUT, consumer, we want each one of them to run in parallel. So if you look at our previous code for the OR gate, what we had basically done is we had defined A, B, and Y. And then we gave A value, B value at the same time, and then waited for the timer. But so the assignment of A and B over here happened in 0 time. Whereas now, since this is operating at a different data rate and this might be operating at a different data rate or a different bandwidth, we might not have this data coming at the same time. And we don't want to have a situation where A is available, B is still not available, and we block producer A until B becomes available. So we want both of them to run independently, generate their own data, and provide this. Okay, now given that that is our constraint, let us start going through our RTL. So this is our implementation of an OR gate with an interface. So we have A data, A enable A ready, B data, B enable B ready, Y data, Y enable Y ready. These are the input output signals. Our first step is to create a wrapper over this. Go to our wrapper folder. We copied this as IFC test. And then we copied this the second time around as the instantiation of our IFC or the simple regular expression to convert this to ports. Define our layers. We are going to give this a unique name so that this does not conflict with the wave that we generated for the OR test. Now, one additional thing that we do in this file is we have defined this clock. So we are going to drive the clock in this wrapper itself. Which basically means here we say clock equals to 0 and then forever equals to 9. And finally, end that. And this completes our definition of the wrapper file. And in our make file, we have defined these files for our wrapper. And we have defined this target. IFC test and IFC test. Let us go ahead and focus on getting our IFC test.py. So we start with our OR test. cocotb has got something called as cocotb drivers. So we will just take a look at that. So you have an entity called cocotb bus. If you go into the source, we find drivers. We have a few drivers over here. What we're interested in this. And this defines your bit driver, your base driver class, and your bus driver. And what we are interested in is bus driver. When we speak of a driver class, what this class provides us is with a queue to which we can put in data, and then with a method where we can define our bus signals, let us say A, B, and C, and then have some prefix added to this bus signals to create the actual bus. and then a method which will basically take data from this queue and drive it on our signals. So it will drive on these signals. We will import bus driver from cocotb bus, and at this point we will define our driver class. Our driver class is derived from bus driver. Our initialization routine for the driver class, it takes the DUT, the name of the DUT, and the name of the clock signal as a parameter. What we do is we call our base bus driver. It's in its function and pass the same parameters over there. Okay. So this is our model for our input driver, which means we have enable as an input, data as an input, and ready as an out. So one thing which we are going to do over here in our input driver is we set our enable to be equal to 0, so that our enable value is always driven. And then we register our clock. And out here we define our signals which are specific to this driver. So our signals are ready, enable, and data. This driver class provides a function called underscore driver send. And what this driver send function does is whenever something is queued, it will pick it up and it will send it to this driver send. So let's implement that. So when our test bench has sent us some data to send, we will wait for the ready to go high. And once the ready has gone high, we are ready from our side because we have some data to send. We are the producer. So we assert the enable. So we check if self.bus.ready.value is not equal to 1, then rising edge of, wait for the rising edge. Once we got the rising edge, we assert enable to be 1, data to be whatever value was sent in. Now in our simulation we have got the concept of delta delays. So if we have an always at star block and a number of statements over here, then whatever is there on the right hand side, it is a part of our sensitivity list. And the first time when we enter it, we will enter when one of these elements have changed. Once we exit it, a different always block might fire, which might again change one of these elements, and we might re-enter this always block. Each time this block triggers, it is called as a delta delay increment, and we are not sure as to which delta delay we are in. We wait for all the updates to all this always blocks to finish and that particular delta delay to get over. It is possible that you might have two always blocks, this one and this one. This might have fired, this might not have fired. If you are trying to check multiple different values which come from different always blocks, you might get an error. So we have assigned this. So now we wait for the end of the delta delay cycle. And then wait for the rising edge of clock. Now once we have got the rising edge of clock, our next task is to deassert enable. And after deassertion of enable, we want to wait for a time step increment before we again go back and sample this ready signal. So we wait for. So we have our driver defined over here. Now similarly on the output side, so this was our input driver. On the output side, we have the exact same signaling. The only thing that changes is our driver send function. So what we can do is we can define our output driver. So our output driver can be derived from bus driver or it can be derived from the input driver as well. If it is derived from the input driver, it will basically inherit the same signals. Let us derive it from the bus driver. Keep the code the same. Signals are these: init, enable, clock. Now in the driver send function, we again wait for ready, and here we are not assigning the data. We are taking whatever data value we got. Okay, so we commented this out, and here we are doing a callback. So whatever data we got, we are sending it out, which means here we need to have and then define. So what this basically means is that at this point, we take whatever this data value is there and we pass it out of this function. So this defines our input driver and output driver. The next step for us is out over here. at the top level of our test. So in this design, we have clock and reset. We have taken care of the clock in our Verilog wrapper. We'll take care of the reset over here. So one thing to be careful about reset is that when we define a reset, we need to ensure that we have both the falling edge as well as the rising edge defined. And the reason for that is whenever we write a design with an asynchronous reset, we say always at pause edge clock or neg edge clock. Now, if we have some kind of a clock gating circuit in our design, due to which the clock is not changing at the time of reset, and we only had the rising edge of reset, we didn't have this falling edge, then we will not enter this block at all at the point of reset. We never saw pause edge clock, we never saw neg edge clock, we will not enter this block, and in our simulation, whatever registers are there, they will not be initialized. If we miss this and we had a free running clock which was triggering this block, then we will not enter this block on neg edge. We will enter it on pause edge of clock, and once we enter this block, since our reset is 0, we will go ahead and execute the reset function. So to ensure that we enter this block whenever the reset occurs, we need to ensure that there is a falling edge as well as the rising edge. So let's do that. This is initially 1. Wait for some random number of time. Then make this 0. Then maybe wait for some more time. Then and now make this 1. Okay, so we have taken care of our reset now. Now we have to instantiate the drivers. So we have input driver, and this takes 3 values we saw: DUT, name and clock. So DUT name will be A and clock will be clock. Similarly, B driver, which takes DUT B, and this is, and finally we have our Y driver, which is an output driver. This also takes DUT Y, DUT dot clock, and our callback. And what our callback function is going to do, it is going to assert that your actual value and expected value, they match. We define this as a global variable, and now our y is the expected value, and we change it to a list. And now here in our for loop, we have a and b driver taking the value of ai and bi. We don't need this, and we don't need this. Now finally we need to wait until all the elements in the scoreboard have been tested. So while length of expected value is greater than 0, wait, wait for some time. And down here we have defined this driver send, but there was no append which is happening to the driver. So we are appending to A driver, we are appending to B driver, but nothing is being appended to Y driver. So let us just do that over here. Just some dummy value gets appended so that this gets triggered. And now since this is entered only once, we always stay in this. We never exit this routine. So what we have done is we have instantiated, we have created our class for input driver, output driver. That is this logic over here. And we have instantiated them over here. Then in our for loop, we have modified the assignment to an append so that it appends it to this list inside this driver. And then we are waiting for all the expected values to be received. So let us just run the simulation and see how it works. No module named cocotb bus driver, it is drivers. ifc.vct, and let us see what's happening in the design. The design has never gone beyond the very first delta delay. Let us see why. For some reason our timestamp is not advancing, and here we should have advanced the timestamp at this point. So let us look into our wrapper code. We have not put a delay over here. So let us say 5 seconds. 0 ticks. Okay, so let us look into why we are getting this segmentation fault. So this is task number 3. So task 3 was our output driver task. And let us, this should be over here. Then let us check our callback. This we call back output driver scoreboard function actual value equals to expected value. Scoreboard matching field expected value is a list, so we do pop 0, and this is a global variable, so we pick it up from the global stack. And with that, let us run our test. And we got an error. Let us open up the waveform. Why enable has never got to 1. And the reason our enable value is not going to 1 is because we have not specified dot value. So now if we run make, we get test passed. If we reload our waveform, we see A data, A enable. On this cycle it is 0, this cycle it is 0, this cycle it is 1, and on this cycle it is 1. B data is following the pattern of 0, 1, 0, 1, and Y data is following the pattern of 0, 1, 1, 1. And this is the exact same waveform which we had for our XOR gate. The only difference is that we have some delays between the enqueuing and dequeuing of different data. Instead of having it after every time unit, we have some delays which come in because either the consumer is not ready or the producer is not ready. This completes our discussion on interface. While we were discussing interfaces, we made multiple mentions of delta delays. You can find cocotb's internal timing model in this particular document. So github.com cocotb wiki timing model. cocotb bus, you will have to read through this code. The code is readable, and this code basically gives you details about the bus components, that is the drivers, monitors, and scoreboards. The difference between drivers and the main difference between drivers and monitors is that drivers change the signal values in your DUT, whereas monitors just observe the signal values. So if you wanted to write a class where you are just observing the signal value and not doing any changes, you can use a monitor class. It has a very similar syntax to the bus driver class. Instead of bus driver, you say bus monitor. You won't have any of this driving logic, so you will just wait for your trigger signal and then wait for all the delta delays to stabilize, and after that you will sample the signal. Now, one of the things that I normally do as a part of my verification effort is, instead of
waiting for read only, I trigger all my signals on the neg edge clock. So for example, here we have rising edge clocked logic. So instead of that, if I write my BFM code as a falling edge triggered logic, it takes care of all the uh, read only and next time step events that we are forced to put in to ensure that our signals are stable, because any signal that has changed at rising edge by the time of falling edge in your simulation, it would have stabilized. In your gate level simulation with delay annotation, it might not have stabilized by falling edge, so you might still have a problem over there. The next item that we need to cover is functional coverage. So we will again take the same design and we will go into details of functional coverage. In the meanwhile, there is one more assignment which you need to complete. When you sign up for the assignment, the README document for that assignment will have details